Good morning, and welcome to the second day of Looking Within, a conference where we've tried to put together many of us who are approaching perhaps this unique phenomenon called consciousness from various perspectives. Yesterday, our approach stemmed mainly from physics and the physical sciences, and in some sense, we looked without to try and understand what is within. Today, biology will be our perspective, both of humans and of animals. There are, I think, several clarifications that I should perhaps make here, and that may, in some sense, set the tone for the day's discussions. First, one of the principal problems that biologists have always had to struggle with was the stranglehold, or what appeared, or appears still, to be the stranglehold of physics, especially as far as the philosophy that guides the understanding and practice of biology is concerned. This was, of course, especially true in the early days when people also looked at biology as the science of the mean, just as the physical sciences tend to do. And it's only with time, I think, that we've realized that biology is actually the science of the variance, not so much of the means. And I think that's an important point to remember. And physicists, in some sense, and I'm using my own term here, and I may be wrong, but in some sense, physicists are utopian idealists. They are definitely idealists. Whether they're utopian or not might be a perspective of a mere mortal like me. But biologists, on the other hand, are common sense realists, right? And this is a thought that started perhaps with Ernst Mayr, who made it very clear that the philosophy of biology has to be looked at very differently. Let me just tell you a little incident, a story here about this. So Professor Srikanthan, whom you heard yesterday, and I have always had this debate, and he had, of course, been always trying to impress upon me the importance of vacuum, which he also talked about yesterday. And he said, do you know, Anindya, that this table that you're standing at is 99.999999% vacuum. And I said, yes, Professor Srikanthan, but if I kick it, it hurts. My foot doesn't seem to go through. So clearly, therefore, as a biologist, I need to understand the table perhaps a little more differently from how Professor Srikanthan understands it. And therefore, this brings me to an important point. We need to be rooted, like many of the plants we study. We need to be rooted, and one of the best ways to be rooted in the subject is to define it. This, I think, became very clear yesterday when one of our speakers, Dr. Shogini Rao, made this very fervent appeal at one point to the panelists sitting there saying, how do you physicists define consciousness? And I think what that call contained was this thought that for biologists, at least, it's extremely important that we deal with a very, very clear, a very, very functional definition of consciousness in this case. Now, why is that important? It's important because we then can assay the process of consciousness. We can decide whether a particular individual or a particular species is conscious or not. But even more important, perhaps, it allows us to communicate with each other. We need to understand, you need to understand what I mean when I say consciousness. And that's a very, very that's of fundamental importance. Second clarification that I will make is that for us biologists, consciousness, the mind, their various manifestations are perhaps all rooted in the brain, the spinal cord, the nervous system that all of us possess. There is perhaps nothing metaphysical or out of the body for consciousness for biologists. We have indeed come a long way from Cartesian dualism, though much of its prescriptions still haunt us, sometimes even when I do a mundane thing like writing a paper for a referee journal. But that's another story, and I won't get into that. Perhaps it can come up later in the discussions at the end of the day. And that brings me again to what I perhaps understand a little better than I understand most people in this room, animals. Now, given that many species, especially mammals, have nervous systems which are so much like ours, it's perhaps only appropriate and fitting that we turn our examination of complex processes such as consciousness to evolutionary biology. There must be a continuum from them to us. And we need to understand this. We need to explore this continuum. And what will perhaps be revealed is that we are conscious, they are conscious, maybe a little differently. I would think that this process of consciousness, as we understand in humans, may in some of its manifestations, be actually present in animals. The difference might be of degree, not so much of kind. Again, a little story. When I joined this institute, and I was a bit of a curiosity because I studied monkeys, and most other people studied indirectly or directly humans. So Dr. Ramanna, who was our founder director and a man of with an admirable sense of humor, one day we had a group photograph of all the faculty of the institute being taken, and he suddenly called to me and said, "Anindya, come stand next to me. You represent all the other species." Well, perhaps the time has come to look at it a little more differently. Perhaps there is not us and them, there is perhaps us, and we need to understand this continuum. The final clarification. Consciousness, whether we can define it or not, is of fundamental importance to all of us. It is what gives us meaning. It gives us meaning to our lives that we lead. It is what makes perhaps life worth living, and sometimes not. And given this fundamental importance, most likely making consciousness a very prime material for natural selection, and given the fundamental continuity of nervous systems that I was talking about, it is entirely possible that other species reflect on their lives and actions as well. Most authors are convinced that other species, other than humans, are perceptually conscious. In other words, they may have mental states like we have. But what seems to be a problem is our understanding of whether they are also reflectively conscious, whether they can reflect on their actions or lives. And I would like to suggest here, and this is not my thought, there have been other people who've thought about this well before me, this problem is entirely methodological. Much of what I understand or what you think about is what you tell me, and animals cannot tell me what they are thinking of. And so, my hypothesis is that if I spend the entire day with you, which I did largely yesterday, not uttering a single word, would you be able to interpret from my behavior whether I was reflectively conscious? And my argument is that you wouldn't. And so perhaps, if we don't find the so-called reflective consciousness, which has for a long time been the holy grail for animal consciousness research, if we don't find it, it could simply mean that we have no way of finding out whether they have it. And this could be a fundamental problem in the science that we do today. It may be overcome another day. Perhaps Nicole Ellis's work is in that direction. But till then, perhaps, we should entertain another possibility. And I will leave you with this thought. Do we need the concept of consciousness at all, especially with regard to animals? Are we hindering the process of understanding this phenomenon in animals by having this unique term, consciousness, to which we must all subscribe, to which we must define and understand in terms that we have so far defined for humans? Perhaps we will have more light than heat, as has been the story in the past. If we did away with this idea, perhaps we need to look at all the underlying processes that define consciousness, maybe the executive functions of the brain, and that might perhaps finally resolve that last frontier. It might finally bring to the fore the continuum that exists across all forms of life, what evolution acts upon, and that final frontier may then fall. Thank you. So I would now like to invite Dr. Robert Hampton, who has very kindly agreed to chair the first session, and he will take it from there.
Introduction and orientation to our session today. I think that puts us on good grounds to get started. And so I want to introduce Dr. Anil Seth, who is a reader in the Department of Informatics at the University of Sussex, and he's also the co-director of the Sackler Center for Consciousness Science. Another notable thing about Dr. Seth is that he is also the program chair for the 16th annual meeting of the Association for the Scientific Study of Consciousness. I think he's interested in having everyone else be interested in that meeting and coming to the UK for that. So without any other comments, Dr. Seth?
Rob, and thanks very much to the organisers for inviting me to participate in this extremely interesting meeting. I was born and raised in England, but my family is largely from India, so it's a great personal pleasure to be here today. So I want to talk about measuring consciousness in humans and other animals, and I'm going to focus actually more on a human case than the animal case, and in that way maybe provide a bit of a segue from what we were hearing about yesterday to what we're going to hear about in the remainder of today's session. Just a word about the Sackler Center, if I might, for 30 seconds, because I think it was commented a few times yesterday that especially in maybe the hard biological physical sciences, it's still quite unusual to come out and say, oh, look, we're really interested in consciousness as opposed to cognition, mind, or whatever. And we now at Sussex University have the Sackler Centre for Consciousness Science. It's been up and running for about 18 months or so. And the aim of this centre is really to connect the basic science underlying conscious experience, a mixture of biology, physics, maths, and so on, with its clinical application. So we work very closely with the medical school to try to understand and better diagnose and treat psychiatric and also brain injuries from the point of view of their disturbances in consciousness. So there are beginning to be some centres explicitly now dedicated to consciousness science. So I want to start with thanks to Dr. Mayank Mehta yesterday, who put up a slide about some working assumptions, because this is a very interdisciplinary meeting. I think this is a very important thing to do. And I don't want to defend or argue for these. They may be wrong, but this is just to help you understand what it is that I'm going to say. So this is where I'm coming from rather than the ultimate truth. Consciousness exists as a natural property of the universe. Consciousness, for me, is a process, not a thing or a capacity or a potential. Humans are conscious some, but not all of the time. I think there are times when we are not conscious. General anesthesia, deep dreamless sleep, and so on. At least some non-human animals are conscious, some, but not all of the time, echoing Aninja's comments just then. Consciousness depends on parts of the brain. I think this is very fundamental. Maybe other things as well, but certainly the brain is important. Here's one which may conflict a little bit with some of what we heard yesterday. I don't think we as yet have any reason to appeal to new, strange, or physics or even quantum mechanics to make progress in understanding consciousness. Consciousness depends on the brain. Biology is a study of the brain, and we can try to connect that to the phenomenology of conscious experience without, at the moment, trying to develop a whole new sort of physics to try to understand what consciousness is. I'm a bit worried for a while that we have this problem that people think consciousness is very mysterious and quantum mechanics is also somehow quite mysterious. So, hey, they must have something to do with each other. And I'm sure that may not be the case, but it's always a little worry for me. Experiences are real, but what they depict may not be. So an example of this would be something like out-of-body experiences. I firmly believe people have out-of-body experiences. That does not mean that there has to be a physical basis for consciousness is outside the body. It means you have to explain why they have that experience. And because we can now induce these kinds of experiences reliably in the lab, we can study them without leaping to the conclusion that because they have such and such an experience, what they're experiencing is the case. So give neuroscience a chance is my sort of slogan for this. We can make a lot of progress using standard physics, biology, maths, in understanding the relationship between the brain, the mind, the body, and consciousness. So what I will try to cover in the next 25 minutes or so is why measuring consciousness, why worry about measurement. Two kinds of measures, behavioral measures, but more importantly, I think for me anyway, brain-based measures. I'll introduce a couple of these, which I've been working on for the last few years. One is causal density, and one is integrated information. This derives from the work of Giulio Tononi in Wisconsin. These are designed as quantitative ways of assessing the level of consciousness in the brain after having established appropriate benchmarks. And then I will try to extend this approach a little bit beyond the human case, tell you something about the work I've done a little bit in assessing animal consciousness, non-human animal consciousness. So why think so much about measurement? Well, having a dependable measure of consciousness, I would argue, is vital for mature science of consciousness. The history of science has told us repeatedly that in order to understand an apparently mysterious phenomenon, we need some way to measure it, to measure whether it's present or absent, its degree, its characteristics, and so on. There's a beautiful book by Hasok Chang called, I don't know if you can see this, called Inventing Temperature. And it was all about how fundamental the role of a development of an accurate thermometer was in catalyzing our understanding of heat, the physical basis of heat as mean molecular kinetic energy rather than something else that might flow about in the physical world. Without a thermometer, a well-calibrated thermometer, we were really kind of stuck. And there was a huge controversy at the time about, well, how does one develop a thermometer in the absence of knowing certain fixed points in temperature. And how do you get those fixed points in the absence of a thermometer? So this is very complicated problems, and for a while they really contributed to a sense of mystery about the phenomenon of heat. And of course now we don't really suffer from those ambiguities anymore. We have reliable thermometers. We know what heat is, more or less. So what would the equivalent be? Well, here's David Chalmers, famous philosopher of mind, demonstrating, this is quite a while ago now in Arizona, this thing. It looks like a hairdryer, but it's actually a consciousness meter. And he designed it to point at your head, and it would tell you how conscious you are. And unfortunately, this particular device has been lost and never been recovered. So we can think of the current enterprise as the reinvention or reverse engineering of David Chalmers' consciousness meter. I don't know if you can see, it says here, how can we search for the neural correlates of consciousness? It would be a lot easier if we had a consciousness meter. So any talk about consciousness must, of course, tackle the problem of defining it. And again, I don't want to spend too long on this because it would take forever. This is a broad definition. I hope it's something most of us would find reasonably intuitive. There are two ways of looking at it. Consciousness is the appearance of a world. From Thomas Metzinger, I like this. Without consciousness, there is nothing, simply nothing at all. There is no world, there is no self, there is nothing. It is the existence of a phenomenal scene for an agent. Another way to think of it is consciousness is that annoying time in between naps. And this brings up an important point, that there are times when we are not conscious, when we are in a dreamless sleep, perhaps. Not all sleep is without conscious contents, but some. I think I'd like to do a little bit better than that in terms of defining and draw two distinctions which are important. One is between conscious content and conscious level. So on the one hand, when we are conscious, our conscious experiences are populated by a range of phenomenal contents. This is a picture from the cover of New Yorker. This person here is having a lot of different kinds of experiences, words, pictures, all kinds of things, thoughts, beliefs. These comprise the contents of a conscious scene. There's also conscious level, which one can think of as scale from being completely unconscious, as in general anesthesia, brain death, coma, and the like, to being vividly alert and awake, as everybody is right now, with midpoints, of course. There's also an important distinction, and this is particularly relevant for non-human consciousness, between primary and higher-order varieties of consciousness. Other ways of thinking about this are phenomenal consciousness, access consciousness, reflective, non-reflective. Often there's slightly different terminologies, but they point at more or less the same thing. That is, that it's possible to draw a distinction between somebody having an experience, per se, a perceptual experience, a conscious scene. In this case, this man is having a conscious experience of a tomato, but because he's a normal human being, let's assume, he's also aware that he's having this experience. He can reflect on this experience and therefore report about it and tell us that he's having an experience of a tomato. And of course, we rely on this methodologically, but it doesn't mean that ontologically we have to have this reflective component in order to have an experience per se. And of course, animals may not be able to do this part, which is why we may have trouble in establishing whether they're conscious in the first place. So I'll come back to that later on. There is a relationship between conscious level and conscious content. Generally, one can think that as one goes up conscious level, from coma, anesthesia, deep sleep, light sleep, drowsiness, then the range of conscious contents increases. When we're vividly, when we have a high conscious level, we can experience a broader range of conscious contents. Also, typically, our physiological arousal level increases. So we become more physiologically alert. But there are cases where this doesn't happen. So, for example, in the vegetative state, patients are typically physiologically aroused. They go through sleep-wake cycles, but they do not seem to be at all conscious. So one can move off this diagonal, and REM sleep perhaps moves off the diagonal in another way. So that's a bit of definition. Now, two kinds of measures, behavioral measures and brain-based measures. Starting with behavioral measures, one can think of three different ways of using behavior to try to assess what somebody is conscious of. One can use objective measures, which might be the ability to choose accurately under some forced choice conditions. You know, did you see something or not? Did you see A or B? One can use subjective measures, typically. This is what's done, where you ask subjects whether subjects know that they know or see something. So you might ask them to make a judgment whether they saw A or B, but then how confident they were in that judgment. If they have high confidence in saying that they saw something, then one usually infers that they actually did see it and they're not just guessing. On the other hand, if they say they're guessing, then there's no particular reason to assume that they had a conscious experience guiding their behavior. And then there's, of course, introspective measures, where we can ask subjects to report their experience directly. What is it that you're experiencing right now? And introspection has got, over the last century or so, quite a bad reputation within psychology, and I think largely unfounded. It's data, it's first-person data, but it's data that's essential for the study of consciousness. Most behavioral measures have to do with content rather than level, but there are a few exceptions. So one can establish behavioral scales for distinguishing various clinical disorders of consciousness, such as coma and the vegetative state. I won't go through I don't have time to go through it here. Just a point. If anybody's interested in this, one of the things we've been working on in my lab lately are different behavioral ways of trying to assess whether a patient might still be conscious even though they don't display any behavioral signs of it. In this case, by assessing their residual ability to learn various simple contingencies. And this is something we can now take into the clinic to try to figure out, in cases of brain injury, whether patients might be candidates for further treatment. Problems with behavioral measures are two, really. There's a lack of specificity. So for objective behavioral measures, if you just ask somebody to make a forced choice decision, that could be mediated by unconscious responses. So we know that one can make above-chance discriminations. This is typically done. Blind sight, a great example of this, without there being any corresponding conscious experience. There's some controversy over blind sight still, but let's assume that it is what it says it is. And for subjective reports, where you ask people directly what they experience or whether they have confidence in a judgment, there's a lack of sensitivity. So some subjects may be unable to provide accurate subjective reports. They may be perceptual conscious experiences they're having that they're not able to sufficiently articulate using the kinds of subjective measures that we provide for them. So there's a distinction here between primary and higher order. Something might be primary conscious but not higher order. If it's not higher order, then you can't really provide a subjective report. And patients, again, can have compromised abilities to provide this kind of verbal report. So moving on now to brain-based measures, back to the hairdryer, there's a long history of biological, physiological signals that have been used to try to characterize whether somebody's conscious or not. This goes back to at least to Hans Berger and the inventor of the EEG machine in the late 1920s. Here's one of the early EEG machines who discovered that, indeed, when you're awake, your EEG signal is generally high frequency, low amplitude, desynchronized, and when you're asleep, you have these low frequency oscillations. So quite distinctive signatures. This has been, now we have things like the bispectral index in clinics, which use various components of the EEG signal to give you a number between 0 and 100. How conscious are you? But there are some cases where this index doesn't work particularly well. We can also look at evoked responses in the EEG signal. I'm going to go through this quickly because it's not really the focus of the talk. There's been a lot of discussion about whether synchrony between different brain areas, especially long-distance synchrony, in particular frequency bands, is a good indicator of consciousness or not. Widespread activation and repeated observation, especially using functional MRI, are that stimuli that not processed consciously activate sensory cortices, but only locally, whereas stimuli that are reportably conscious, that we say that we see, also activate a very broad network of frontal and parietal regions. Of course, the problem here is, are those regions involved in conscious report or in conscious experience per se? Hard to distinguish those two. What I'm going to focus on, though, is something that comes more from an observation of what the phenomenology of being conscious is actually like. Can we say something formally about the phenomenology of being conscious and come up with a corresponding measure that we can apply to the brain? Another way to phrase this approach is to expand a little bit on what's become the standard approach in consciousness science, which is to identify neural correlates, activity in groups of neurons or brain regions that has a privileged relationship with consciousness. This slide comes from Christoph Koch. Here's the world, here's the brain. The idea is that part of this guy's experiences of a dog, and we might be able to find somewhere in the brain some process set of neural dynamics that is always there when this person is having an experience of a dog and is never there when they're not having that experience. So it's a perfect correlate. But of course, that's not totally satisfactory. We can identify a correlate, but then there's this idea about, well, there's still some magic going on, because how does one get from a correlate to the experience? And this At the one extreme, you can think of this as the ever-present hard problem of consciousness. How do you get experience at all? But there's another way to understand it, which is, well, where's the explanatory link? You can have a correlation, but a correlation by itself is not an explanation. But one can try to find correlations that have explanatory power and explanatory purchase. And that's not saying the same as we have to solve the hard problem. That's saying, how do we connect neural dynamics to features of conscious phenomenology in a way that makes explanatory sense? And we can do that without necessarily worrying about why experience exists in the world in the first place. So I suggest we can look for these sort of things called explanatory correlates, which are brain processes that account for aspects of conscious experience. And so these measures would have a greater specificity, because one would have an independent reason to believe that a brain process has something to do with the conscious experience if it explains something about that conscious experience and doesn't just correlate with it. So let me give you an example of the kinds of things that I think we can try to formulate formal measures of, deriving from phenomenology. Dynamical complexity is the main focus. I'll come to that in a second. But we also experience the world from a first-person perspective. We have this unique first-person point of view on the world, an interaction between egocentric and allocentric frameworks, and we generally relate all our experiences to a sense of self. Our experiences are shaped by emotion, mood, volition, and agency. And we also have a subjective sense of reality of the world, most of the time, that we accept that what we experience is real. But I'll focus just on one of these aspects of phenomenology I think we could try to account for. And this work was really inspired by earlier work by Gerald Edelman and Giulio Tononi. I spent quite a few years in San Diego working with Gerald Edelman. Tononi had left by then. And in the late 80s, they wrote I thought what was a wonderful paper in Science, pointing out something about conscious experience that I hadn't recognized before, which is that every conscious experience that we have is both integrated and differentiated. And what I mean by that is you probably haven't seen this picture before unless you've seen me talk before. It's a Korean painting. But you're having a specific experience now of this picture combined with the text and the sound of my voice and the temperature of the room and so on. This is a single experience which is different from every other experience you've ever had in your life and will ever have again in your life. Every experience is a unique event. Every experience rules out the simultaneous occurrence of an enormous repertoire of alternative possible experiences that you could be having right now. It's highly unique. There's a lot of information having this experience right now that you're having. At the same time, every conscious scene is integrated. It's perceived as a unified scene. You do not experience various bits of it and separately. We experience every scene as a unified whole. And over a characteristic timescale, every experience shades into another, equally differentiated, equally integrated experience. Even the experience of a black screen is equally informative in that it rules out just as many alternative experiences. It's not just about the complicatedness of a picture. It's how many things are ruled out by the occurrence of a particular thing. One way to think of this quantitatively is that this balance between integration and differentiation picks out what one can think of as the terrain of complexity, which is a bit of a weasel word, a bit of a difficult word, but somehow systems that are completely differentiated but not integrated can enter lots of different states, but there's no unity to them. Similarly, systems that are very, very tightly coupled element to element are highly integrated, but cannot enter a large number of different states. So we want to find ways of describing systems that are able to combine or conjoin integration and differentiation. Perhaps if we can find measures and then begin to relate them to brain dynamics, we can start to make progress in connecting phenomenology to measures of the brain. And quite interestingly, once one's got a phenomenological insight like this, one can start developing various different ways of characterizing it mathematically. And I won't go through these different approaches, it would take too long. But the interesting thing is they are subtly but significantly different and provide alternative testable hypotheses for what the neural dynamics underlying consciousness might be. And I'm going to talk about a couple of them in a little more detail. But just to drive the basic point home a little bit further, one can think of a photodiode as let's assume, not conscious. Why not? Well, it's not, for many reasons, hasn't got a brain, but one reason is it's not sufficiently differentiated. A photodiode can only enter two states. The world is either light or dark. That's it. A digital camera, on the other hand, can enter a very large number of different states, one for every visual scene for which it's facing. So it's highly differentiated, not as much as the brain, but still much more than a photodiode. But of course, at one level of description, a digital camera is nothing more than the collection of lots of independent photodiodes. This picture is only a picture for us looking at it. It's not a picture for the camera. So a camera is not sufficiently integrated. And the thought is that the brain, or the parts of the brain underlying conscious experience, are both differentiated and integrated somehow in virtue of the kind of structural and dynamical connectivity that one observes, especially during conscious states. This condition here. So Gottfried Leibniz said something very similar several hundred years ago, as with all good ideas, which is that the most perfect world is the one in which there is the greatest diversity in combination with the greatest order and harmony. Okay, so I'll spend a couple of minutes now talking about a couple of these measures. One that I've been working on for a while is called causal density, and this is based on a very nice concept which have adapted from, with several other neuroscientists, from econometrics. And it's a way of assessing whether one variable can be said to causally influence another variable. So this is back to very standard mathematics statistics now. And the basic idea is we can say that x1 causes x2 if the past of x1 helps predict the future of x2. This is Clyde Granger who made the concept usable. The concept goes back a long way. He won the Nobel Prize in Economics partly for this work about 10 years ago now. So the idea is, causality is usually based on precedence and predictability. So a cause has to precede the effect, and in this case, a cause also has to carry information that helps predict the effect. And the important thing is, if x1 causes x2, x1 has to carry information to help you predict x2. More than is already available just in the past of x2 by itself has to carry additional predictive information. And one can formalize this in various different ways. The standard way is by using linear autoregressive modeling. It's a very standard mathematical technique. Basically, you can model both of these time series together as weighted combinations of a certain number of previous observations, and then you can drop one of the time series and see how much your error changes, and if your error changes by a lot, then you know that this time series carried relevant information. So that's Granger causality. It's actually used in lots of contexts besides consciousness. In fact, the other strand of my work is really about using this kind of thing to identify causal interactions in data generally, especially in neuroimaging data, to try to describe functional networks. One can generalize this concept to deal with multiple multivariate situations. It's very nice, and this would be a different talk about the different ways one can extend this concept to make it useful for neuroscience, and we've done quite a lot of work lately on these methods. Causal density, then, if you think of a system composed of a number of different elements, and one calculates the Granger causality between each pair of elements conditioned on the rest of the system, and then one just calculates a fraction of these interactions that are significant, statistically significant. And that's causal density, very simple measure. But it captures exactly the kind of property that we're looking for, because if all the elements are independent from each other, then wherever you look, it's not going to help you predict what's going on anywhere else in the system, because everything is independent. So your causal density will be zero. On the other hand, if all the elements are doing exactly the same thing, then again, it doesn't matter where you look. There's no additional information to help you predict what's going on anywhere else in the system. So again, your causal density will be zero. The only case in which causal density will be high will be those cases where different parts of the system are doing somewhat different things, so they can contribute potentially useful predictive information, but at the same time, the system as a whole is globally unified, so that knowing what's going on somewhere in the system is useful for helping know what goes on somewhere else in the system. So you pick out this middle ground. And we've done some simulation studies, 5 minutes, okay, of this sort of measure, showing how it behaves in various models. Again, time prevents going through it, but basically one can see that in fact this measure behaves according to one's intuition, that it's maximized for this middle ground of dynamical complexity. Here's a study by another group where they calculated Granger causality between implanted EEG electrodes, and again showed high causal density when a patient was conscious of seeing something as opposed to not. Skip that. I think I'm going to... Well, for those of you who've heard of integrated information theory from Tononi, I don't have time to go into it. It's a similar idea, trying to operationalize this idea that a system generates more information than the sum of its parts considered independently. So very similar insight. And again, the challenge is to find ways to actually develop practically applicable measures of this. And with my postdoc Adam Barrett, we've been working on this too. And I think I'll skip the maths there. We don't have time for it. But the important thing is that these measures roughly do indeed capture the same intuition, but they do so differently. So they behave slightly differently, at least in the simulation model. So they provide different candidate hypotheses when applied to neural data. So in the last 5 minutes, I'll just tell you about some recent work applying this stuff in practice. We've been looking at anesthesia, EEG data required under anesthesia. At the moment, we're just looking at 2 areas: source localized EEG to the anterior and posterior cingulate, high-density EEG. 8 subjects underwent propofol-induced anesthesia, and we just wanted to look at what happens to the Granger causality between these 2 areas and compare it to, say, some other measure like phase synchrony between these 2 areas as a function of anesthesia. And there are lots of methodological problems with applying something like Granger causality to EEG data. One has to be very careful about satisfying the various assumptions of the method. And again, I don't really want to get into that too much. But the basic point is that the method is applicable to stationary stochastic data. So you can't have data that's changing too much all over the place. The take-home message, just summarizing this, I'll tell you it in words, is that, in fact, bidirectional Granger causality increases during loss of consciousness in these studies uniformly across all subjects, and particularly in the beta and gamma bands. So here's something, here we have an observable objective fact, at least in this study, about what happens in the brain when one loses consciousness. In this case, Granger causality goes up. And when we compared this to what happens to phase synchrony, which had been looked at in a previous study that originally acquired this data, we found that Granger causality was much more consistent across subjects than the phase synchrony measurement, which was quite nice, provides a bit more confidence in the measure, and allows us to relate it to these concepts like causal density. This paper in PLOS One actually just came out today, so you can look at it today. You couldn't have looked at it yesterday, but you can see it today. And so on the face of it, having this increase in Granger causality between areas may not be consistent with this idea of increased causal density during consciousness. One might expect to have less causality as you lose consciousness, this sort of functional disconnection as you lose consciousness. Here we're seeing a functional increase in connectivity. But this is because this is still quite early days in this kind of data. We're only looking at 2 areas, and these particular regions are part of what we call the mesial highway in the brain, which conveys slow waves during sleep and anesthesia. And so what we now need to do is look at more than 2 regions to see as a network property what happens to things like causal density and integrated information. But the way is clear, very clear to doing this now, and to comparing it to other standard measures like synchrony. So in the last couple of minutes, I'll return to some stuff about beyond the human, mammals, birds, and cephalopods. With David Edelman, we had an article in Trends Neurosciences a couple of years ago now, setting out a few issues in assessing animal consciousness with special attention to animals that maybe people don't think of so much, like the octopus. The octopus, fascinating creature for many reasons. But studying animal consciousness is hard because we rely generally in studying human consciousness on accurate verbal report of what people experience, as I said just earlier. Back to this. We rely on people being able to say that they saw a tomato, whereas maybe an animal might have an experience of a tomato but not be able to tell us what they saw. So how do we get around this? This is an epistemological problem, not an ontological problem. How do we get around it? Well, the approach that we suggested, at least for mammals, is by recognizing that, in fact, humans and mammals share a very large neural substrate relevant to consciousness. Specifically, you can see things like irregular low-amplitude brain activity when they look like they're in an awake state, involvement of thalamocortical circuitry, lots of homologous neural circuitry there, and rich discriminatory behavior suggesting links between perception and memory. Basically, the idea is you can take humans as a benchmark, look at what we know in humans, and see how much of that behavior and neural machinery and neural dynamics is conserved in other mammals. And in mammals, certainly, there is high level of conservation. And then one can try to see whether other properties of consciousness in humans one can also map onto neural dynamics or brain regions and look again for homologs in other animals. Moving beyond mammals, it becomes a lot harder because brains become more different. So in the case of birds and octopus, it's very difficult to know, especially in the octopus, what is the equivalent of a thalamocortical system, where there's no thalamus, there's no cortex. We know very little about the octopus brain. Nonetheless, the octopus brain is pretty large and complex, and octopus behavior, to the extent it's been studied, really well studied in the 60s and 70s, less so lately, is really, really complex and interesting too. They can do all kinds of weird things. So here we need to think much more carefully about how to draw analogies between humans and these more distant, phylogenetically more distant creatures. And by coming up with greater sort of explanatory mechanisms for consciousness in humans, they can be more transferable. So if it turns out that causal density or integrated information is a very useful way of characterizing consciousness in humans, that's more transferable to some of these other creatures. One can think of a sort of phylogeny of consciousness like this. Just to show you what we know, the avian brains, one can make quite a lot of useful comparisons with mammalian brains. The octopus brain is kind of a mystery. With David Edelman now, we're beginning to do some, if you like, octopus psychophysics to try to get at some ground truths about how octopuses perceive and respond to different stimuli. Do they respond, for example, to point light motion of prey items like a crab here? And here's another experiment that David did where we have a real crab and a video crab, and we monitor whether the octopus makes an attacking motion towards the crab. So you can start to pick apart what octopuses respond to, and then you can start to do interesting things like, are there equivalents to binocular rivalry, all kinds of psychophysics. So this is just to show you that I think there are ways to get at these complicated issues of non-human and even cephalopod consciousness. And this was a slide from the ASSC a few years ago. Where do we stand with respect to evidence of consciousness outside the human domain? And evidence varies, but one can characterize it along a scale like this. So to summarize, I've emphasized distinctions between conscious content and level, between primary and higher order consciousness, different kinds of measures, behavioral and brain-based. For subjective measures, behavioral ones, it can be very hard to distinguish measures of primary consciousness from the ability to report about what it is we're experiencing. For objective measures, it can be very hard to guarantee that a given measure is mechanistically tied to consciousness, problem of specificity. So the approach is to operationalize objective explanatory correlates, find things going on in the brain that explain something about a particular experience or a particular class of experiences, guided by subjective measures, guided by what people say about what they experience. So I've given an example of one class of these measures, dynamical complexity, that conscious scenes are both integrated and differentiated. Introduced two specific ways of testing for this property. And the challenge then is to apply this reliably to humans and then in extension to challenging cases such as infants, brain damaged patients, animals, and perhaps even machines. And for animal consciousness to use humans as a benchmark and extend outwards, taking care not to confuse metacognition or higher order consciousness with perceptual consciousness per se. So thanks to my postdocs, Adam Barrett and Lionel Barnett, who did a lot of the mathematical heavy lifting. There are PhD positions available in the group if you are interested in coming. Actually, probably much more relevant to the rest of the day, this book just came out with Cambridge University Press, all about modeling natural action selection, and a lot of it is about monkeys and the like. So maybe that might be also of interest to some of you. And the last word is about this consciousness meeting we're organizing in Brighton next year. It's the ASSC. These meetings have been going on for 16 years. They're along with meetings held in Arizona. It's one of the two main conferences on consciousness science internationally. It's held in Europe once every 3 years. We already have lots of keynote speakers. The call for abstracts is open right now, closes in about a month. So please consider coming. We are in Brighton, which is, here's London, here's Brighton. It's very easy to get to. Well, I mean, from here, it's not so easy, but it's definitely possible. You can get to London Heathrow, get a bus down to Brighton. Brighton's a lovely place. It's very close to central London. It's vibrant, scientific, artistic, digital communities, known for beach life and nightlife, and minutes from the South Downs National Park. Here's the beach. Here's the pavilion. Here are some shops. Here's a pub. Here's the countryside. In summer, it's even warm, sunny, and it doesn't even rain a lot, despite what you may have heard about England. So next July will be a beautiful time to come and see us. We're going to be in this wonderful venue in the heart of the city, which is where Pink Floyd debuted The Dark Side of the Moon, for those of you who know that. So we have a great heritage there too. And everything in Brighton is within 10 minutes walk, from the train station to the beach to the venue to all the bars, restaurants and shops. So I very much hope to welcome some of you to Brighton in the summer, and I'll just leave you with these summary slides here. Thank you very much.
Well, thank you, Anil. So we have about 6 or 7 minutes for questions. If you have a question, please come up to the microphone and maybe state your name as you speak.
I have several comments. Like when you are talking about the conscious state, the wakeful state, but the same gamma band is present both in REM sleep and wakeful state. Moreover, in some of the dream, people are conscious that they are dreaming. So some sort of consciousness is there, even in REM sleep.
Yeah, I agree. I mean, certainly REM sleep, for me, is a prima facie example of a conscious experience. And yes, when you're lucid dreaming, you're also aware that you're dreaming. That's true.
And the methodology you have used, like Tononi and Edelman, that has been severely criticized. They used mutual information, which is conceptually wrong.
Well, I'm not using mutual information. That's partly why I'm doing what I'm doing, because I agree with those criticisms.
What you have done, you have written h of x minus h of x, condition of A.
No, I didn't even get time to talk about that. Most of the causal density stuff is based on autoregressive modeling using Granger causality, which for Gaussian variables is equivalent to transfer entropy, not to mutual information, so it's directed. One of my main worries about mutual information is undirected. And to get around that, I wanted to use measures which are statistically directed. They represent causal interactions.
In one of your slides, you have used those kind of...
Well, that was a description of integrated information, which is also directed. It uses mutual information between the states of systems as they evolve across time, not between states at the same time.
Even methodologically, that is not the right way.
Well, we don't have time to... Well, we can talk about that later.
Let's make sure we have time for a couple of questions.
Oh, okay, sure. One more question. When you use causal density, can you do it for embryo? Because in embryo, the synaptic organizations are not being ordered. So after a certain time when synchronizations comes about, then you can probably use causal density approach.
Well, let me say, so one of the motivations for causal density is I wanted to develop a measure that would not just be high for highly synchronized states. Because as we know, if you're in an epileptic seizure, your brain is totally synchronized, but you're unconscious in epileptic absence. And one of the problems with some of the other measures is that, okay, if they're based purely on synchrony or indeed mutual information, they're going to be maximal for those cases. So causal density and particularly causal density designed that it will be very minimal in those extreme cases. So that's one thing. The second thing, can you apply it to embryo and so on? Well, you can apply it to any multivariate data set. The question is, can you interpret it for a given data set? And this is why we're being extremely cautious in how we apply it. So the data I showed, the only thing we published just came out today, was to 2 source localized areas from EEG. But we spent a year trying to just make sure that the data was sufficiently clean, sufficiently interpretable, that we could be confident in our result about what's happening at the level of Granger causality. So now, yes, what I would like to do is apply it to a range of cases from patients, infants, wherever we can get this kind of high time resolution data source. You can't do it with fMRI. It's not enough time resolution. But it's a case of establishing the statistical validity of the method, not a particular data type, I think.
Yeah, thank you. Let's move to the next question.
Yes, thank you. Thank you for your very clear and inviting talk, even to Brighton. And, well, I am a French philosopher, phenomenologist. So I would have 3 small questions to you. The first one, coming back to your working hypothesis, I was wondering why and if yes, how you would include among your working hypothesis the phenomenological first-person level, because you said, for example, that brain is somewhat related, or consciousness is somewhat related to the brain, even if we don't know how. First, you began with that, and I was wondering why you would not, how you could agree to to add to your working hypothesis phenomenology and first-person conscious level? So that's a very small first question.
That's a very big question, but...
Yes, well, maybe you can just answer quickly.
Okay, well, so point of the working hypotheses were that I was not going to commit to defending them right here. However, I will say that with respect to understanding the first-person perspective, I think the way I would try to do that, and this is in work that I've been doing right now, is on trying to do stuff about what makes the world seem subjectively real in terms of prediction of sensory consequences of action. Because I think it's this predictive element that is really grounded, rooted both in exteroceptive perception and interoceptive perception of the body, that underlies the sense of self, that underlies the first-person perspective. But the point there would be that there's not one size fits all. So just as with the history of life, people didn't come up with a single thing that tells you whether something is alive or not. There's a collection of different properties that living things have. First-person perspective is a different property for at least human consciousness. It might have a different explanation. Here's the first stab at a model of the subjective sense of reality, which involves predictive mechanisms underlying integration of interoceptive, exteroceptive signals. That, for me, is one approach, very influenced by people like Thomas Metzinger and so on, that way.
Yeah, okay, thank you. Maybe we'll talk that.
Okay.
And
my second point... for just one more question, actually. So,
okay.
Perhaps we should share.
Purushottama, I deal with speech problems and hearing problems, okay? Thank you for the schema that you are providing. My question is, you are referring to somebody's explicit information about consciousness. That's one of your ways of getting information from the subjects.
Mm-hmm.
Now, speech itself can be at different levels, like if you take Piaget's level, how a child would recognize.
The extent, basically the options that you give people about how they use speech, or it doesn't have to be speech, it can be a behavioral response as well. Press the button if you see a stimulus, and of course that they have to understand the rules of the game, so they have to understand the instructions. But I completely agree. There's a lot of subtlety in exactly how you phrase the way in which you verbally elicit information about somebody's subjective experience. I mean, I'm influenced a lot these days by Claire Petit-Mongeon and people like that, about using structured interview techniques to try to get a more objective second person, if you like, not first or third, second person description of phenomenology in cases like synesthesia. And then in psychology, we've looked at, you get very different effects. For example, whether you ask somebody, are they confident in their judgment about seeing something, or are they confident in having seen something? These things sound quite similar, but they're actually quite different. So you have to be very careful in the questions you ask.
But is it important that we go to the level of neurology that we are all talking about? How is it important whether it is in the cingulate gyrus, frontal brain, or reticular formation? It's not important that we go through the processes than locating it.
Well, I think, you point to a main important problem, which is how do you distinguish the neural mechanisms underlying consciousness from those involved in report, in verbal report, speech comprehension, and the like? This is a methodological problem. It's not an ontological problem about the mechanisms underlying consciousness, I don't think. Maybe I don't understand your question.
My question is...
I think that's great. We probably need to move on. I'm sorry to interrupt, but we can discuss later, and let's move to the next talk. Please, thank you, Dr. Seth, very much.